Hello, and welcome to our series of quantum computing videos, which we hope to train you about um, quantum computing over a set period of time. So let's go right into talking about regular computers. Regular computers basically store and interpret binary ones and O's. A computer basically is a device that can be instructed to carry out sequence of arithmetic or logical operations with a computer program. Modern computers have the ability to follow generalized sets of operations called programs. These programs basically enable computers to perform an extremely wide range of tasks, which would be called algorithms. A complete computer system would include hardware, an operating system, peripheral equipment, which would consist of a mouse, a keyboard, a screen, and so on. And that would be considered a fully operational system. What has happened over time is the term has kind of evolved a little bit, and it has become used interchangeably for operations of a whole group of computers that are connected and that work together. In particular, a computer network or computer cluster. With that being said, the fundamental basis of electronic digital computing is the ability to store a binary value of 1 and 0. A binary value of 1 and 0 is or can be what they consider a little electrical charge or impulse. And what it does is it opens and closes gates based upon its property. When you're looking at a computer keyboard and you look at the letter A or B or S or D or whatever letter you're looking at, that consists of 8 bits, which is 1 byte. So 8 binary bits, or 8 ones and O's, equals 1 byte, which is 1 keystroke or 1 letter. It's a little bit different when quantum computing. In addition, regular computers have electromagnetic properties, which quantum computing in a way does as well. Also, regular computers, they run on a chip for processing, and quantum computers do as well. The problem with regular computers is they can do a lot of things, but they are capped at the amount of speed that they are limited to. So let's look at some of the history of how things unfolded, so to speak, with quantum computing. So during the first half of the 20th century, physicists discovered the laws of quantum mechanics. And the laws of quantum mechanics consist of things that are really small, really well isolated, or very cold. Okay? With quantum computing, we are using the laws of quantum mechanics, which are the 3 I just listed above. The quantum mechanics apply to the behavior of subatomic particles. So an electron or photon, for example, can be said to be in any one of several what they call quantum states, depending upon such characteristics as the spin on the particle. In 1981, we had physicist Richard Feynman come up with a proactive idea that basically stated that if quantum properties could be read and set, a computer could actually use an electron or a photon or other particle to store not just a single 1 or O, as we spoke of before, with the bits and bytes, but a number of various values simultaneously, because you're dealing with 2 electrical impulses. So to give you an example, let's think about 2 pennies spinning for a moment. When 2 pennies are spinning, we cannot guess their actual state. We don't know if they're heads or tails. So If they fall, they can fall in many different states. They could fall as heads, 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 tails, tails, heads, and on and on. But the problem is when they're spinning, we can't really tell what their state is, although we know their state is between 1 and 0. This is very similar. This is exactly what happens to quantum computing, and we use these values called qubits, okay? And that's short for quantum bits. And in 1985, another well-known physicist, David Deutsch, was at Oxford University, and he basically fleshed out Feynman's idea by creating an actual design for a quantum computer, including an algorithm to run it on. Now, for that time, that was very progressive. At the time of Feynman's proposal, the techniques for manipulating individual atoms or even particles had not yet been developed. So practical quantum computing could not be built, or computers could not be built. However, during the 1990s, considerable progress was made. And it was spurred in part by the suggestion of a man at Bell Labs named Peter Shor, which algorithm, it outlines a quantum algorithm that could be used for rapid factoring of extremely large integers. So you're looking at powers to the number of whatever, so n to the number of 100, or factoring extremely rapidly. And basically what happens is a working quantum computer could actually break modern public key cryptography and all types of other things very rapidly because of this, because of the two states of the qubit, because it could either be between 1 and 0 and 1 and 0 on both sides, moving, rapidly back and forth. And so the reason for the tremendous potential power of quantum computing is that, especially with 3 qubits, could store 8 values. And in general, for n qubits, one can operate on n2 to the n power values simultaneously. This means that a single quantum processor might be able to the equivalent of a large number of separate processors. So clearly, many problems that have been considered not practical to solve may be able to be tackled with quantum computers. A variety of promising techniques for implementing a quantum computer proposed, and many have been pursued experimentally. This includes the use of superconducting circuits, trapping of ions, or neutral atoms, which is the latter in an optical lattice, and they were called quantum dots. So they were using the spin of electrons, which is what we're still thinking about when we're thinking of quantum computing, is how things spin, as my example before of the pennies. If they're spinning, we can never really tell what state they're in. Said, you can kind of see how quantum computing branches off of physics and the idea of quantum mechanics, and kind of works its way into this idea of using qubits as opposed to using bits and bytes. Okay, so a bit and a byte would give you a 1 and 0. A qubit gives you 2 unknown states or known states, but they spin at a rapid pace. So we would, it could be any 2 states. So hopefully you learned a little bit about the background of quantum computing and where it's come from, and we will move on to some of the more detailed items in our next videos. Thanks. Have a great day.